Well, we finish up this section of review in section 4 in the review chapter by going over how to simplify complex rational expressions. You had complex fractions in your algebra days where you had a fraction within a fraction in the numerator and or denominator. Well, a complex rational expression is pretty much the same thing, only with necessarily with rational expressions. It's an expression that contains one or more rational expressions in the numerator and or the denominator. There are two usual techniques or methods to simplify because we don't want to leave a fraction within a fraction. We want to simplify our expression for better understanding. And the first method involves getting the complex rational expression so that it's just a single rational expression over a single rational expression, which might mean that you might have to actually add or subtract the rational expressions in the numerator and or denominator first. And then we will invert and multiply and simplify our answer. I'm going to do that method with the first example. The second method is if we multiply the numerator and the denominator by the LCD of all the rational expressions that are within the overall complex rational expression. Once we do that, we distribute, we simplify, and in both cases, both methods work. Sometimes one maybe is set up a little bit better than the other. So for the first example here, I'm going to use this method, and I'm going to add the numerators, subtract the denominators. My common denominator in both cases would be 7y. So I'd have to multiply top and bottom here by y. So that would be y over 7, y plus, here I'd have to multiply top and bottom by 7. That would be 7 over 7y. All over, multiply top and bottom here by y. I would get y squared over 7y. Multiply top and bottom here by 7. I would get minus 49 over 7y. So this becomes y plus 7 all over 7y all over y squared minus 49 all over 7y. Well, this is a rational expression divided by a rational expression. So I invert and multiply y plus 7 over 7y times the reciprocal. Now I'm going to factor this numerator that's going to be my denominator. It's going to factor into y minus 7, y plus 7. It's a difference of squares. 7y up here. Well, you can see all the 7y cancels with all the 7y here. The y plus 7's cancel out, top and bottom, so that just leaves 1 in the numerator and 1 times y minus 7 times 1 in the denominator, and that would be my simplified answer. In the next problem, I'm going to kind of approach this one using the second method, but before I do, I am going to rewrite this as 4 minus 6 over x all over 2 over x minus 3 over x squared. The negative exponents, of course, we know what that means, and so I'm going to rewrite those so that my exponents are positive. And now what I'm going to do is I'm going to find the least common denominator of all these rational expressions within this. Now this denominator is 1, this is x, this is x, this is x squared. My LCD is going to be x squared. I am going to multiply the numerator and the denominator by x squared. X squared times the numerator all over x squared times the denominator. And I'm going to distribute here, and with a little luck, this is going to simplify. I end up with 4x squared, didn't give myself very much room, minus x squared times 6 over x gives me 6x. On the bottom, I'm going to distribute x squared over 1 times 2 over x, the x cancels here, leaves 2x, minus the x squared times the 3 over x, the x squareds cancel, and leaves minus 3. And it looks like I'm comfortably done here, but the numerator factors. So sometimes you have to simplify these. This is going to factor with a GCF of 2x, and again, oh, wait a minute, 2, I factored a 2 out, 2x minus 3. Got to be careful and factor it right. And you can see why. I have that common factor, so I end up with 2x over 1, which is just 2x. That thing really simplified down nicely. All right, the next expression, if you're wondering why we have such a weird looking one, is because of calculus. We're going to be doing some limits later on in this class, but we're going to get into limits big time in calculus. And you're going to get expressions that are going to be kind of unusual looking like that when we talk about the derivative and the limit definition of a derivative. So in this case, I'm going to use the second method again. I'm going to multiply. There's only one. It's this guy right here. I mean, that's over 1, that's over 1. There's only one rational expression within the rational expression, and the denominator is 1 plus h. So I am going to multiply by 1 plus h, top and bottom. So I have to distribute here. I don't really need that over 1 part. 1 plus h times 5 over 1 plus h. That's going to cancel the 1 plus h's. It's going to leave 5 minus, and then 5 times the quantity 1 plus h. And on the bottom here, nothing cancels. That's going to give me h times the quantity 1 plus h. Now I'm not going to distribute in the denominator, but I am going to distribute in the numerator. Careful with that minus sign. That gives me 5 minus 5 minus 5h all over h times the quantity 1 plus h. These are going to cancel out. That's just going to add up to 0. So I'm going to get a negative 5h all over h times the quantity 1 plus h. Well, you can see why I didn't distribute in the bottom. I have it factored form and the h's cancel. They're a common factor top and bottom. So this thing simplifies all the way down to negative 5 over 1 plus h, or if you'd like, h plus 1. Now, there is a little bit that they talk about in this section that has to do with radicals, and that is something that we highlighted a little bit on the section on radicals, but we're going to go ahead and just quick review, and that is rationalizing the denominator. We do not want to leave a denominator with an irrational number or irrational expression in the denominator, so I am going to, if you remember, multiply by something top and bottom that's going to make the square root of 7 into a rational number. And that is itself. I'm going to multiply top and bottom by the square root of 7. Now up top, the square root of a radical times the square root of a radical. You may remember the square root of a times the square root of b is equal to the square root of a times b. So this is the square root of 21. On the bottom I have the square root of 7 times the square root of 7, which is 7. Square root of 7 times square root of 7 is the square root of 49, which is 7. Now, you cannot cancel the 7 and a 7 out of the 21 because the 21 is underneath the radical sign there. That's as far as that goes. My denominator is a rational number. I've rationalized my denominator. Now, in the second one, I have two square roots with a subtraction sign in between, so I can't do it quite as conveniently as this example. I'm going to use the conjugate effect. Remember, if there's a sum or difference, you're going to want to use the conjugate effect. The conjugate effect. The conjugate is the square root of 13 plus the square root of 10 over the square root of 13 plus the square root of 10. I think the conjugate effect is something if you're in prison. I don't have to swear to that. Let's see here. I'm going to distribute up here. I have, well actually, for right now I'm going to leave the 12 out in front. I can distribute my last step if I need to. Something tells me I'm going to want to leave it like that for right now. But in my denominator, remember a minus b times a plus b is a squared minus b squared. So, by doing that, the o and the I cancel and FOIL, and the square root of 13 minus the square root of 10 times the square root of 13 plus the square root of 10 would be the first terms, that'd be 13, minus the product of the last terms, that'd be 10. It's a good thing that I did leave this 12 by itself. I have 12 times the quantity of the square root of 13 plus the square root of 10 all over 3. And isn't that convenient? Since it's already in factored form, I can go ahead and cancel the common factor of 3. That leaves 4 on top times this expression over 1. I'm not going to put it over 1, so just times the square root of 13 plus the square root of 10. Now if you want to distribute on that, that's fine. But there was a lot in this section, a lot of stuff, especially with adding, subtracting, multiplying, and dividing rational expressions, complex rational expressions. It's going to take a lot of practice, practice, practice.